So now we will discuss about the sensing principle. Means in fact, sensors, what they sense, how they sense. So basically, there are three, in general, two things. One is electricity that we can sense. From this, we can sense the voltage variation in voltage, current, etc. The second is the magnetism, by which we can sense something. So that's why we will go through the sensing principles, means how sensors senses and what they sense. So the first one, we will see electricity, how a particular sensor can sense electric signals, means voltage or current, etc. So the first element, if we consider the capacitor, uh, it's a very useful physical phenomena in sensor designs toolbox. So the capacitor, it can be used to measure the distance, area, volume, pressure, force, chemical composition, etc. So it can be used in different sensors to sense these inputs, means distance, area, volume, pressure, force, chemical compositions. So how capacitor can be used to sense? We will discuss this one. So although I know you are familiar with the working of capacitor, how it accumulates charges on it, how it allows current through it, and all the things. So I will just revise the thing. Let us consider a capacitor. Okay. So it can be characterized by the magnitude of charge on either conductor. As we know that the physical structure of a capacitor, it may be a parallel plate capacitor or cylindrical capacitor, like that. So any type of capacitor, how it can be characterized by magnitude of charge on the conductor and by the positive potential difference between the conductors. So the ratio of charge to voltage is constant for each capacitor. So that is given by C equals to ratio of Q to V. And this C is called the capacity of that particular capacitor. Means how much charge can capacitor hold? It can store. So now when this capacitor is connected into an electrical circuit, what happens? It may present a complex resistance to that electrical source. Suppose electrical voltage source is connected across two ends of the capacitor. So definitely it will present a complex resistance that is equals to, as given in this expression, V by I equals to minus 1 over j omega c, where j, a complex number, its value is the square root of minus 1, and I is the sinusoidal current at a particular frequency, angular frequency omega. Otherwise, its frequency will be 2 pi fc. So omega is 2 pi fc. Correct. So this I is the sinusoidal current of frequency f or angular frequency omega. We may also represent this capacitor by an alternative method, that is the ratio of the dimensions of the capacitor. So C can also be expressed as epsilon naught A by D. So epsilon, in fact, is the dielectric constant of the media that exists between the plates of the capacitor. So in a capacitive sensor, the value of capacitance is the measure of stimulus. Stimulus means the input that we want to measure. And how we can measure, that depends on the capacity of the capacitor. So C is the measure of the stimulus. So to change the capacitance, the stimulus needs to change one of the parameter that define the capacitance. So the parameter is A by D, where A is the area of the plates and D is the distance between these two, separation between these two plates. So wherein one of them will change the capacitor value, which can be measured quite accurately by an appropriate circuit. So in this way, the capacitor can be used as a sensor element, and we can sense a particular type of input, maybe anything, particular stimulus that can be sensed using capacitor. The ratio E to D may be called geometry factor for parallel plate capacitor. Now we have different types of capacitor. I hope when you studied the capacitor during your BTech first, second semester, then you have seen different types of capacitor in lab. Parallel plate capacitor, electrolytic capacitor, cylindrical type capacitor, paper capacitor, etc. etc. So this capacitance, as I mentioned, C equals to epsilon A by D is for parallel plate capacitor. Two parallel plates are separated by a distance D, and the overlapping area of this parallel plate is given by A. And between these two plates, air is the medium. So epsilon is the dielectric constant of air. If we have a cylindrical capacitor, as shown in this figure 1, A, where there are two cylinders. One is of radius A, second is of radius B. Correct. So for these two cylinders, we can treat them as two different plates. One is this one, second is this one. So for these plates, the cylindrical capacitor, the capacitance can be given by this expression. C equals to twice pi epsilon L divided by natural log B by A, where B and A are the radii of the inner outer cylinders and L is the length of the cylinder. So what is considered here? The L is very, very large than B. So in this case, this is the capacitor value. Now, these capacitors can be used to measure different stimulus, can be used to sense different input signals. For example, here, uh, sorry, in figure this B, the inner cylinder is this one, outer one is this one. If we move the inner cylinder, then overlapping area will change. So if overlapping area changes, means the ratio of B by A changes. So what happens? The capacitor will definitely be different. So depending on this change, we can measure the displacement easily with the help of capacitor. So this capacitor can be used to sense the displacement. So that's why it can be used as sensor. Okay. Now in this formula, uh, the length L, L length means the overlapping length. So as shown in figure 1, and this ratio means 2 pi L logarithmic of this. This is called factor for the cylindrical capacitor. In case of parallel plate capacitor, the geometry factor was just A by D, ratio of A by D. But here it is this one. So a useful displacement sensor can be built with such a capacitor if the inner conductor can be moved in and out of the outer conductor. According to above expression, the capacitance of such a sensor is in a linear relationship with the displacement. So if we look at this figure, there are two capacitors, the outer one, the inner one, and this overlapping length is represented by L. So if inner capacitor of radius A, outer capacitor of radius B, if we move this inner capacitor in and out in this outer capacitor, so what happens? Because of changing this length A, the capacitance of capacitor will be different. So, if we calibrate this displacement with respect to the voltage stored by the capacitor, directly we can measure the capacitance, or we can say directly we can measure the displacement. So, this capacitor can be used to measure the displacement. Now, this is one thing, means by changing either A or D or the L, we can get different values of capacitors. So what we can say, we can use this to measure different types of stimulus, different types of input signals with the help of capacitor. Now the second thing is the dielectric constant. Dielectric constant is also present in the expression of capacitor, as we have seen. The capacitor is expressed as epsilon naught E by D. So keeping A and D constant, if we can change the value of dielectric constant, then again we will have variable capacitor. So that can also be used to measure to sense some other inputs. So the increase in capacitance due to the dielectric presence is a result of molecular polarization. So because of the molecular polarization, we can change, we will get the different values of capacitance. So we get an expression for the capacitor with dielectric C equals to K Q by V naught, where this Q by V naught is represented by this C naught. C naught is the capacitance. For the parallel plate capacitor, we thus have the value of this C as epsilon naught K into A by D. Where what is C naught? C naught is just equals to epsilon naught A by D. So C naught is the capacitance of parallel plate capacitor, and the dielectric between the parallel plate is just epsilon naught. But if we have some other dielectric between these two parallel plate capacitors, the capacitance will differ by this term K. Okay, so now it is dielectric dependent. So, in more general form, the capacitance between two objects may be expressed through a geometry factor, that is the ratio of A by D in case of parallel plate capacitors, and it is given by expression this one, 2 pi L natural log V by A inverse for cylindrical capacitor. So this is the geometry factor G. So generally we can express the capacitor of any object by epsilon k into g, where g is the geometry factor, and that depends on the shape of the object, means plate of plates, whether it is the parallel plate or a cylindrical type of capacitor, and their separation means how much they are having the distance between these two. Okay, so depending on the shape of the object, we have different types of capacitors. Dielectric constants must be specified for test frequencies and temperature. Means the dielectric constant, it also depends on the frequency that we are going to apply through across this capacitor, and temperature of environment as well. Means at which temperature the capacitor is present. Okay, sorry. So some dielectrics have a very uniform dielectric constant over broad frequency ranges. For example, polyethylene. Okay, so these type of materials, if we construct the capacitor and insert these material between the plates of capacitor, then such type of capacitor can be used for a broad range of frequencies, because its capacitance, the dielectric constant doesn't depends on the frequency. It is not changing with respect to frequency. That's why for a broad frequency range, it can be used. While others display strong negative frequency dependence. That is means negative frequency dependent means on increasing in frequency, dielectric constant of capacitor decreases. So depending on the nature of materials used between the plates of the capacitor, we may select the application of these type of capacitor, whether they can be used for a very large range of frequencies, or for frequency ranges where we need the variation in dielectric constant with respect to frequency. So this variation, dielectric constant versus temperature, is shown in figure 2. So here, what is depicted? The dielectric constant of water, means if water is filled between two plates, and if temperature changes, the environment temperature changes, our temperature changes due to some other reason. What happens to this dielectric constant? So this dielectric constant decreases. On increasing temperature, dielectric constant decreases. So the dielectric constant decreases means the capacity of the particular capacitor will also decrease. So based on that, we can measure some stimulus. We can sense some input signal. Now, in a good capacitor used in electronic circuits, a dielectric constant K and geometry G better be stable. Means what we need for a capacitor to be used in electronic circuits. What is desired? The geometry means ratio of A by D or logarithmic of B by A inverse, and the epsilon or the K. Okay, it should be stable, means it should not depend on frequency or the temperature. Means with respect to change in frequency and with respect to change in temperature, these two things, means geometry of the capacitor and the dielectric constant, it must be stable. But it is true for what? Electronic circuits. Okay. Ideally, they should not vary with temperature, humidity, pressure, or any other environmental factors. So good capacitors are critical factors that determine quality of electronic circuits. So when capacitors are used in electronic circuits, how much circuit is stable, how much circuit gives perfect response, that depends on the quality of capacitor. So what are the qualities? Means it's geometry, dielectric constant between the plates of capacitor. It must be stable, means it should not depend on the temperature, humidity, pressure, environmental factor, frequency as well. Okay. However, if we want to design a capacitive sensor, what we need to make a bad capacitor. We don't need a good capacitor. Good capacitor must be stable. But in case of sensors, if we want to design a sensor that is using capacitor as a sensing element, or that should be based on the measurement of capacitance, then what we need? We need a capacitor must be a bad capacitor, means whose value varies with temperature, humidity, pressure, or some other stimulus. So that's why we could sense these things. So if capacity changes with temperature, we can say this sensor is a temperature sensor and it is based on the measurement of capacity. So capacitive sensor can be used as a temperature sensor if these two values are depending on the temperature. Similarly, they can be used as a humidity sensor or pressure sensor and so on and so on. So in case of sensor designing, what we need, a very important thing, capacitor must be a bad capacitor. But for other electronic circuits, it must be a good capacitor. Like the wristwatch, the digital wristwatch. Okay, a small power is given to this digital wristwatch from a pencil cell or from a point type of cells. So if capacitors are used in these cells, if these capacitor, their capacity depends on all the temperature and all other things, so this will vary. So capacitance will change, and you will not get the accurate reading. So that's why in electronic circuits, what we need a good quality capacitor. But for when capacitor is used as a sensing element, what we need, this capacitor must be a bad capacitor. Okay. So by allowing a capacitor's parameter to vary selectively with a specific stimulus, one can build a useful sensor. Okay. So what is the meaning of sensing principle? Means what is the principle? How we can sense something? So first thing is, if the sensor is designed based on the capacitive sensor, uh, we will sense the capacitance uh, using these principles. Either sensing uh, the capacity that is depending on the ratio A by D. So by varying either A or D, we can sense different values of the capacitance, or by sensing the dielectric constants. So this sensing principle involved in these type of sensors that are using capacitive elements as a sensor elements. Now we will discuss a particular example of capacitive sensor. Suppose we want to sense the water level in a tank. Capacitor can be used to sense the water level. If we want to mm, turn it on, means so that the tank can be filled by the water, or if we want to stop the tap, so that if water is reached at a particular level, uh, the tap will stop automatically. So for that we can use this capacitive sensor. to sense the level of water. Here it is used to sense the water. In place of water, we can take any other type of liquid. Okay, any liquid. So we can sense the capacitance. We can sense the level of any type of liquid with the help of capacitor. Now, as shown in here, in this tank, the three different heights are mentioned in figure A. Let's first one is H naught. H naught means below this or from 0 to up to H naught. No capacitor line means no capacitor is present in the tanks. After H naught to capital H, the capacitor cylindrical type of capacitor is present. Okay. So when the level increases, means water fills more and more space between the sensor's coaxial conductor. Cylindrical capacitor means there are coaxial conductors. One is inner conductor, one is the outer conductor. And if tank is filled with the water, what happens? This inserted inside earlier in these two conductors, now the air is replaced by water. So because of the dielectric properties of air and water, the capacitor definitely will change. Correct? So, thus changing the average dielectric constant between the conductors and subsequently changing the sensor's capacitor. So, if we want to sense the capacitor, so that capacitance will definitely change, and that will depend on the level of the water. So, after sensing and putting a particular threshold, we can stop filling the water in the tanks or we can drain it out depending on the requirement. The total capacitance of this coaxial sensor is expressed as C of small h equals to C1 plus C2. It is equals to epsilon naught Z1 plus epsilon naught K times G2, where this epsilon means epsilon naught. It is the dielectric medium between the plates of the capacitor, and that is air. Okay, and G1 is the geometry of the capacitor. Means this there are two types of capacitor. One that is filled, the plates of this capacitor filled with the water, and second when they are filled with air only, there is no water. So these two capacitors are corresponding to these two regions. Okay. So C1 is the capacitance of water-free portion of sensor and C2 is the capacitance of water-filled portion. The corresponding geometry factors are uh, designated G1 and G2. The total sensor capacitor can be written as CH equals to twice pi epsilon naught natural log B by A within the bracket capital H minus small h into 1 by k. Simply we can derive this formula based on the earlier two formulas. Okay, we can derive it. It's very easy. So we will have this type of capacitor where this small h is the height of water filled portion of the sensor. Now if the water is at or below the level h naught, the capacitance remains constant because small h is 0. If we look here, means if water level is below this, means h naught. So this small h is 0, correct? Here small h is 0, the capacitance will be given by this one. Okay, and this will remain constant. There will not be any change. So, if water is inserted inside this cylindrical capacitor, its capacity will change, and we can change directly. We can sense directly the capacity, and that capacity is proportional to this height. So, what we can, in fact, sense the height level of the water, how much water level is present in the tank. So, we can directly sense it. So, this is figure 3. It shows the water level capacitance dependence. It is a straight line level from H naught. Since the dielectric constant of water is temperature dependent, as we have seen in earlier figure, the capacitive water level sensor shall be combined with temperature sensor. For example, thermistor or register temperature dependent device (RTD), which would monitor water temperature for compensating the temperature dependence. The appropriate temperature correction may be performed by the electrical signal conditioner. What is uh, the meaning of this? Suppose we want to design a water level sensor based on the capacitance. Okay, but what happens? The tank is placed in open area. Sunlight is coming to the tank directly. So still the capacitor will change the water level, no doubt. But what happens when sunlight comes? Sunlight, the more intensity is present, the water heat or temperature will be different at different times. So that will change the capacitance, the electric constant of the capacitance. So that's why there must be a compensating device to avoid the errors. Correct. So what we can do, we can insert a resistance dependence device or temperature sensor that will compensate this error. Also directly we will get the level, means how much water level is present. Uh, Correct. So if there is no temperature dependency, then there is no problem. But it is true, the water level, the dielectric constant of water, as shown in this figure, it is decreasing with increasing temperature. So here we will have different values of this K, and that will not give you the correct capacitor. That will not give you the correct height. So to compensate that, we should have some compensating elements. Okay. So this is the meaning. So this was the capacitor sensor to change the displacement, water level, etc. etc. Now we can use this capacitor sensor as a humidity sensor. So I mean another example of a capacitive sensor is a humidity sensor. So in such a sensor, dielectric between capacitor plates is fabricated of a material that is hygroscopic. That is, it can absorb water molecules. So when the material absorbs water molecules, material dielectric constant varies with the amount of moisture. So now, what happens? The dielectric constant will directly depend on the moisture contents of the molecules. So, in directly, the capacitance, the capacitance can be expressed in terms of the humidity. Correct. So accordingly, what we can see, if we look at the earlier formula, so we can write according to that formula, the capacitance can be written as epsilon naught kg, where this k is the dielectric constant and it varies because material, it absorbs the water molecules. So that's why this k will be different. Okay, so this changes the capacitance that can be measured and converted to a value of relative humidity. This figure 4 illustrates the dependence between capacitance and relative humidity of such a sensor. The dependence is not perfectly linear, but this usually can be taken care of during the signal processing. Means the change in humidity means the absorption of water molecules, and in fact the uh, it may be proportional to the relative humidity value, but it is not always relative. But we can take this care, just like if you have seen the potentiometer. Potentiometer is nothing but a variable resistor. It varies when we move a knob from one position to other, maybe from anti-clockwise or clockwise. But that variation is not linear. So although it is not linear, but we can take the care. And always, if we move the knob from one position to other, the instrument will always show the exact value of the resistance. So same thing can be taken care here. Although the dependence of humidity and the change in the dielectric constant ultimately change in the capacity is not linear, but we can take care of using some specific signal processing mechanism. So this figure is showing the transfer function of capacitive relative humidity sensor. So here is the humidity level, percentage of relative humidity, and here is the value of the capacitance. So now if we the graph, it's not exactly linear. In this portion, it is not exactly linear. Here it is not exactly linear, but roughly we can say it is linear. Well, in a particular region, when it is not linear, we can apply some signal processing condition, and we will say the relative humidity is proportional to change in the capacitance. So we can design a capacitance to get the humidity level. This is one example. Now, so by sensing what? The capacitance. And when we sensing the capacitance, in fact, what we are sensing, the voltage is stored across two plates of capacitor. Means it is related to electricity. Correct? So based on the principle of sensing electricity, we can design some sensors like capacitor sensor for different applications. Similarly, there is another phenomena that is known as the magnetism. Electricity, magnetism, they are related. Okay. So a fundamental property of magnetism is that moving electrical charges essentially produce a magnetic field. What does it mean? If we have a wire that carries some electric current. So when current is moving in the wire, the magnetic field will also be associated with this wire. I think you will be familiar with this phenomena. So this is the fundamental property. So if an electric current is capable of producing magnetism, it is possible that magnetism can be used to produce electricity. And that Michael Faraday showed in his experiment in 83. Okay. So what he showed, an ability of varying magnetic field to induce electric current in a wire. So this is the brief about the magneticity. In fact, we are interested in to design a sensor that is based on sensing magnetism or flux, magnetic flux. Correct. So for that, this is the background. Means how the magnetism and electricity they are related. When current carrying conductor produces magnetism, so magnetic field can also produce this what the current. Okay, so that is shown here. So here the electric current is generated as long as magnetic field changes. That you know very well. So Faraday's laws of induction says that the induced voltage or electromotive force is equal to the rate at which the magnetic flux through the circuit changes. If the rate of change is in Weber per second, the EMF will be in volts and it will be given as E equals to minus d phi by dt. This is d phi b, the magnetic flux. Okay. So the rate of change of magnetic flux will be equals to electromotive force, that is the induced voltage. Now, if varying magnetic flux is applied to a solenoid, means a coil type of wire, then the induced voltage is given by V equals to minus capital N d phi by d phi b by dt, where N is the number of turns in this coil. Okay, and phi b is what the magnetic flux, and d phi by dt is the rate of change of flux. The minus sign indicates the induced voltage always opposes this. Now, this equation we can write in different way. V equals to minus n d of B A by dt, where this flux phi is written as V into A. B is what the magnetic field and A is the area of the circuit. Okay, means the coil. So the equation means that the voltage in a pickup circuit can be produced by either changing amplitude of magnetic field or area of the circuit. So if we have a coil where V is the magnetic field, A is the area, N is the number of turns. If N is fixed, either by changing V means the value of magnetic field or by the area of the, we can have different values of voltages. And if we are able to sense this voltage, we can say we can design a circuit that can we can design a sensor that can sense magnetic field. Okay. So in an electric current, if an electric current passes through a coil which is situated, actually in this para, what we are discussing, how we can devise a sensor that could sense or that will be able to sense the magnetic field or magnetic flux, or based on the sensing the magnetism, it can give some values. Okay. So what happens if an electric current passes through a coil which is situated in close proximity with another coil? So according to Faraday law of EMF, in a second coil, the EMF in a second coil will appear. Why it appears? Because current carrying coil will produce magnetic field, and that magnetic field will definitely crosses the second coil. And as I said earlier, when current carrying coil can produce magnetic field, the magnetism can also produce a current. So this changing magnetic field in second coil produces electric voltage. So that is the principle. Okay. So the magnetic field penetrates not only the second coil, means it produces magnetic field in second coils. But what happens? This magnetic field does not penetrate only in second coil, but it penetrates first coil as well. So thus the magnetic field sets an EMF in the same coil where it is originated. This is called self-induction, and the resulting voltage is called self-induced EMF. So Faraday law for a central portion of a solenoid is the induced voltage V, that will be equals to minus of d n phi b by dt. For a simple coil with no magnetic material in the vicinity, this value is proportional to the current through the coil. So the n phi v can be equated as L of I, where L is the proportionality constant, which is called the inductance of the coil, and I is the alternative current or the AC current that is flowing through the coil. Thus, this value V can also be written as minus of L di by dt. So from this equation, we can define the inductance as L equals to minus of V by di by dt. So the several conclusions can be drawn from the above equation. All these equations I hope you are familiar with. Why we have taken this magnetism? In fact, we want to measure this L, means inductance of this. And can we change the inductance of a coil? If yes, then how we can change? And if we change the inductance, if we change that inductance of coil by varying something, so what we can say, that particular stimulus can be changed based on that particular type of sensor, which is sensing the inductance of the coil. So that was the background for this. So what conclusions we can draw? The induced voltage is proportional to the rate of change in current through the inductor. Voltage is essentially zero for DC. If this I is DC current, di by dt will be zero. So that will be zero. Voltage will be zero. No voltage will be induced. The other conclusions, voltage increases linearly with the current rate of change. Okay. Voltage polarity is different for increase and decrease currents flowing in the same direction because of nature of induced EMF, because induced EMF is always opposing force. Okay. So the induced voltage is always in the direction which opposes the change in current. So like capacitance, inductance can be calculated from geometrical factors. For a closely packed coil, it is L equals to, from previous expressions we can say, L equals to this one minus V di by dt. If we put the value of V and di by dt, then what we will have? L equals to n phi V by I. So here n is the number of turns per unit length in the coil. The number of flux linkage in the length L is n times phi B equals to NL into BA, where A is the cross-sectional area of the coil. For the solenoid, V equals to, means magnetic field is given by mu naught into N into I, and number of coil, I is the alternating current, mu is what, the permeability. Then the inductance is given by this expression. L equals to N phi V by I, that is equals to mu into N square L by A. Now it should be noted that L into L is the volume of the solenoid that often is called the geometry factor. So LA is the geometry factor for the solenoid. Thus, having the same number of turns and changing the coil geometry, its inductance may be altered that make an inductive transducer possible. So here the geometry is LA. So if we change either A or L, what we can get different values of inductance. So based on that, what we can say, we can design a sensor that could sense L.